Welcome to chapter 9. This is chemical bonding Lewis theory. So I will show you the overview, what we want to learn from this topic. So first of all, we will look at types of chemical bonds. Then we will talk about electronegativity and chemical bonds. Then we will go on to talk about the dipole moments. Then lastly, we will talk about the Lewis dot diagrams and structures. So as usual, the video assignment has been posted in chapter 8 folder. So you gotta have to check that video assignment. First, let's look at the types of chemical bonds. So in this presentation, we have 3 types of chemical bonds. When metals interact with non-metal, we form an ionic bond. In this case, electrons are transferred from the metal to the non-metal, and this creates a charge that binds the 2 elements or the 2 atoms involved. Then we have another chemical bond where we have a non-metal and a non-metal interacting. This type of chemical bond is known as covalent bond. That's the bond that we are going to focus on in this topic. So for this chemical bond, electrons are shared between the 2 non-metals. The third one is between metal and metal. It's a metallic bond. In this case, electrons are pulled. What it means is that one electron can interact with several nuclei or several nucleuses. The same case, maybe 2 or 3 nuclei can interact with a single electron. So in metallic chemical bond, we have positives at fixed spaces in a sea of electrons, and the electrons are moving around. That's why metals conduct electricity, because the electrons can move around and the electrons are not bound to a single atom within the metal. So that is metallic bond, but we are not focusing on that one in this course. Now, before we talk about chemical bonds, let's look at the periodic table of electronegativities. As a reminder, electronegativity is the ability of an atom to pull electrons towards self in a chemical bond. So if you have 2 atoms, definitely both atoms would want electrons closer to them. But an atom with higher electronegativity will pull electrons more towards itself than an atom with low electronegativity. So in terms of the periodic table, we see that as we go down, these numbers are decreasing. The electronegativity is decreasing as we go down the groups on the periodic table. So you can see here we have group 1. Lithium has higher electronegativity than sodium, which in turn has higher electronegativity than potassium down here. Group 2, we see beryllium has higher electronegativity than magnesium, which in turn has higher electronegativity than calcium. Now if we go to group 7 here, we see the same trend. The electronegativity is decreasing down the group. The same trend is observed here. The noble gases have electronegativity of 0. That's why they do not like to form chemical bonds, because there is no electronegativity in them. Now, what we mean is, let's say we are interacting two molecules. We are interacting lithium and fluorine. And you can see the difference in the electronegativity between lithium and fluorine. Fluorine will pull electrons towards itself. Actually, fluorine will just abstract an electron from here to itself. In the end, we form an ionic bond where we have total transfer of the electron from lithium and fluorine. So we will see what we mean when you talk about electronegativity as we progress with this lesson. Now, what are covalent bonds? Covalent bonds are formed between two nonmetals. So a bond between two nonmetal atoms, or between a semimetal and a nonmetal. So in this case, the bonded atoms may share 1, 2, or 3 pairs of electrons. We'll see what we mean by that. So each pair of electrons is a chemical bond. So if the bonded atoms share 2 pairs of electrons, we'll have 2 chemical bonds formed. If they share only 1 pair of electrons, then we'll have a single chemical bond. And we have nonpolar covalent bonds. So these bonds are formed between identical atoms, or if bonded atoms have the same electronegativity. So if you have 2 atoms, if you have 2 nitrogen atoms, so nitrogen and nitrogen, and you want to form a chemical bond between them, the chemical bond will be a nonpolar covalent bond, because the 2 nitrogen atoms have the same electronegativity. In this case, we won't have a single nitrogen atom pulling electrons towards itself in that chemical bond. The electron would be in the center between the 2 nitrogens. In that case, we have a nonpolar covalent chemical bond. Then we have another chemical bond among the covalent bonds, that is polar covalent chemical bond. This bond is formed when the bonded atoms have different electronegativity. So in this case, if we have 2 atoms like hydrogen and chlorine, or hydrogen and fluorine, the fluorine has very high electronegativity. Hydrogen has low electronegativity. So what will happen is the fluorine will pull electrons away from hydrogen. So if we have such kind of chemical bond, the electrons will leave towards the fluorine and away from hydrogen. In that case, fluorine will be partially negative and hydrogen will be partially positive, as we will see later. So when we talk about covalent chemical bonds, we have 2 types of them: nonpolar covalent bond and polar covalent bond. So there are some rules that we can use to determine whether or not we have a covalent bond or we have a polar covalent bond. So there are 4 rules that we are going to use. What does the first rule say? If the electronegativity difference Usually it's abbreviated as delta electronegativity, the change in electronegativity. So this delta, as we already know, stands for change. Usually called delta electronegativity, is less than 0.5, then the bond is nonpolar covalent. So if you subtract the electronegativities of the two elements and you find it is either 0.5 or negative 0.5, the bond is covalent bond. But now if you do the subtraction and you see the change in electronegativity is between 0.5 and 1.6, that bond is considered as a polar covalent chemical bond. If the change in electronegativity is greater than 2.0, then that bond is known as ionic chemical bond. It means we have involved a total transfer of electrons from one element to another. So that of course leaves us with a problem. What about if the gap between 1.6 and 2? Because here we say from 0.5 to 1.6, and here we are starting only from 2. Then we have 1.6 to 20. What if the two elements have the difference in electronegativity within this? That's when we use rule number 4. So rule number 4 says if the change in electronegativity is between 1.6 and 2.0, and if a metal is involved, then the bond is considered ionic. So if you have a metal and a nonmetal in this case, and the electronegativity is between 1.6 and 2.0, you can be rest assured that you have an ionic bond where you have total transfer of electrons. However, if only nonmetals are involved, the bond is considered polar covalent. So those are the two issues that you look at. Do we have a metal in there and a nonmetal? We say, okay, 1.6 to 2.0 change in electronegativity will mean an ionic bond. If we have only nonmetals, then we have a polar covalent bond. So let's test ourselves. State whether we have a pure covalent or a polar covalent. So a pure covalent is the same as non-polar covalent. So I'll give you some time to answer this question, or you can just stop the video and answer the question before I bring the answer. All right, hopefully we are ready. So in this case, the first one is a pure covalent bond because the electronegativity of carbon is 2.5. The electronegativity of hydrogen is 2.1. So if you look at this chemical bond, the change in electronegativity will be 2.5 minus 2.1, which is 0.4. And this is less than 0.5, which means this is a non-polar covalent bond. What about here? If we look at the two, the change in the electronegativity of oxygen is 3.5. The electronegativity of hydrogen is 2.1. So when you subtract the two, we see the answer is 1.4. So this is a polar covalent bond because the electronegativity is 1.4. We do the same thing here. We subtract the electronegativity of fluorine, which is 4.0, and the electronegativity of hydrogen, which is 2.1. And we see the answer here is 1.9. And remember, this 1.9 is between 1.6 and 2.0. So here we need to decide. do we have a polar covalent or an ionic bond? So the answer is both of these are nonmetals. So since they are nonmetals, we are not having an ionic bond. What we are having is a polar covalent bond, although it is after the 1.6 that is for a normal covalent bond. Now let's look at this. This is nitrogen and nitrogen. So obviously this one has a change in electronegativity of 0. So it is just a non-polar covalent or a pure covalent bond. Now let us define what we call dipole moments. A dipole is coming from the word polarity. So we have two poles of a molecule. We have a positive pole, which is here, and a negative pole. So this molecule is known as a polar molecule because we can say the chlorine side has a negative, the hydrogen side has a positive. In terms of electronegativity, we see that the electrons will stay close to the chlorine and away from the hydrogen. So because the electrons are staying close to the chlorine, this chlorine becomes partially negative. So this stands for partial charge, partial negative charge. Here, this hydrogen is bare because the electrons have moved towards the chlorine. So it becomes partially positive. So in general, we have a polar molecule, and you can see the polarity moves towards the negative atom. So we can look at different molecules. So dipole moment has a direction and magnitude. So we give a number for this polarity, as you will see later. Let's look at oxygen and hydrogen in water. Oxygen is more electronegative than hydrogen. So the polarity will move away from hydrogen towards oxygen. So this is the arrow that we are showing here. The same case here, the polarity moves away from hydrogen to oxygen. That's the arrow we are showing here. When you combine the two movements, the dipole moment will point up here towards the oxygen. So this is the total dipole moment when you add this dipole and this dipole. So these are dipoles for individual chemical bonds, but this is the dipole for the total, for the whole molecule. The same case here. The most electronegative element in this case is the fluorine. So the dipole will point towards fluorine. So what we are saying is this molecule has a net dipole moment. This molecule also has a net dipole moment. Now here we have carbon in between, oxygen this side, oxygen this side. So what's going to happen is the dipole moment will move from carbon to oxygen. But another dipole moment will also move from carbon to oxygen. So because we have the same magnitude of dipole moments, but going the opposite direction, the dipole moments here will cancel each other. So in total, this molecule, carbon dioxide, has 0 dipole moments because these two cancel each other. If this is 1, this is -1. If you add them, you have 0. So we are saying the polarities in carbon dioxide cancel each other. In the end, the dipole moment is 0. Now, let's look at the dipole moment as a number. So this is the symbol for dipole moment, and the dipole moment is measured in dBi, the guy who studied this. Now, if we compare the two molecules, this is ammonia. This is nitrogen trifluoride. So if we compare the two molecules, we see that In this case, nitrogen is the most electronegative element between nitrogen and hydrogen. So the dipole moments will move from hydrogen to nitrogen, hydrogen to nitrogen, hydrogen to nitrogen. So the total dipole moment of this molecule will be moving up. Now when you come here, you have the opposite effect. Fluorine is more electronegative than nitrogen. So in this case, the dipole moment moves from nitrogen to fluorine, as you can see here. Nitrogen, fluorine, and the total dipole moment moves down, as indicated by the arrow. Now, if you look at the numbers, you see the dipole moment is bigger here than in here. So the question is, why is the dipole moment bigger in nitrogen and hydrogen and smaller in nitrogen and fluorine? So before we go there, we said the dipole moments will point towards the most electronegative atom or group. Why does B have a smaller dipole moment? So the answer is both fluorine and nitrogen are highly electronegative, although fluorine is more electronegative than nitrogen. So because both of them are highly electronegative, the difference in their dipole moment should be small. Compared here, nitrogen is highly electronegative and hydrogen is really has low electronegativity. So when you subtract, you get a bigger dipole moment between the two. Now let's look at another molecule. Does this molecule have a net dipole moment? So for a molecule to have a net dipole moment, it should not be symmetrical, or in other words, the dipole moments should not cancel each other. So let's look at this one. Can the dipole moments cancel each other in this case? Now let's think about that. Between carbon and chlorine, what would be the direction of the dipole? The dipole moves from the positive side to the negative side. So we have a dipole moving this way. The same case, we have a dipole moving down here. So this is what we are going to have. So this dipole moving this direction, the dipole moving this direction. If you add the two, the dipoles will cancel each other. So in terms of a dipole moment, we can say that this molecule is symmetrical. This side, in terms of dipole moment, is the same as this side in terms of the dipole moment is the same as this side. You add the dipole moments, they cancel each other, and the net dipole moment is 0. So what we are saying is we don't have the dipole moments for this molecule because they cancel each other. The molecule is symmetrical because the dipole moments canceled each other. Now, if we look at the next example, does this molecule have a net dipole moment? A good question. So to answer this, we need to ask ourselves, is this molecule symmetrical, or can the dipole moments cancel each other? Normally the dipole moments will cancel each other when we have the dipole here equal to the dipole here. So do we have that situation here? The answer is no, we don't. Here we have dipole moment pointing from carbon to chlorine, carbon to chlorine. And in the end, these dipoles are pointing towards the same direction. So they reinforce each other instead of canceling each other. That's what we're going to have. In the end, because this and this reinforce each other, the total dipole moment will move down the middle here. So what we are saying, yeah, we have a dipole moments in this case because the dipole moments do not cancel each other because the molecule is unsymmetrical. That is, the chlorine atoms are on one side and thus reinforce instead of canceling each other. So this is our dipole moment for this molecule. Another question, does this molecule have a net dipole moment? As we can see, the dipole moment here will be equal to the dipole moment this side. Therefore, the dipole moments will cancel each other and will have no dipole moment. Now let's look at ozone. That's the ozone molecule. Does this have a dipole moment? Yeah, because the dipole moves from the positive here to the negative, positive to the negative. So what we are saying is this is how the ozone will be. This part will be negative, this part will be positive. The dipole points down here. So ozone has a dipole moment. Now consider these structures. So the question is, which of these structures have dipole moment? Stop the video, look at them and answer the question. So how you approach this problem is you look for symmetry. Do you have symmetry? If yes, the dipole moments will cancel each other. If no, then you will have dipole moments. So let's look at this one. Do I have symmetry on this molecule? So this molecule is known as a tetrahedral molecule. So what we are saying is, if you have carbon and you don't have any lone pair in them, and you have the same side atoms, here we have 1, 2, 3, 4, the same side atoms on all the fronts, you have symmetry, because this will cancel with this, will cancel with this, will cancel with this. This molecule, as it is symmetrical, so it will not have any dipole moment. While this one is unsymmetrical, because one side has chlorine, the other side has fluorine. So we expect to have a dipole moment on this molecule. What about this? Do we have a dipole moment here? The answer is no. This is symmetrical everywhere. This cancels with this. This cancels with this. And even if we don't go there, carbon and hydrogen are non-polar, so we will not have a dipole moment. What about here? Do we have symmetry here? Are we going to have a dipole moment? The answer is no. We don't have a dipole here because this molecule is symmetrical. This will cancel each other. As I said, if you have the central atom and we have the side atoms which are the same, and we don't have any lone pair here, the molecule is symmetrical. So the dipoles cancel each other. Alright, now you can stop the video, rest a little bit, and then come back to the periodic table. So this is a periodic table. What we are doing with this periodic table is we are showing valence electrons. You can see group 1 has 1 valence electron. Here, group 2 has 2 valence electrons. Group 3, 1, 2, 3. Group 4, 1, 2, 3, 4. Group 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Group 7, 7 valence electrons. And group 8, we have 8 valence electrons. So that kind of periodic table helps us in writing what we call Lewis dot diagrams. So what are these Lewis dot diagrams? Lewis dot diagrams, in Lewis dot diagrams, we represent the valence electrons of the main group elements as dots surrounding the abbreviation for the element. So this is the dot, and this is the abbreviation of the element. 2 dots, abbreviation of the elements, all the way up to here. So you can see that here we're dealing with group 1, group 2, group 3, 4, 5, 6, 7, 8. And the dots will determine the group. For example, here we have 5 dots for nitrogen, which means nitrogen is in group 1, 2, 3, 4. It's in group 5. So if we look at the valence electrons, if you have a valence electron, you see that the electrons are not paired. This is just one electron, no pair at all. If you have 2 valence electrons, the electrons also are not paired. But this can form 2 chemical bonds, because the purpose of a chemical bond is to pair the electrons. So one electron can come to pair here, another electron can come to form a pair here. So it can form 2 chemical bonds. If you have 3 valence electrons, still you don't have a pair. So you can see here 1, 1, 1. The electrons are like single, single, single. 4 electrons, the electrons, we don't have a pair. Single, 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 single. Now pairing starts when you have 5 electrons. So it's like you had 1, 2, 3, 4 electrons. You don't know where to put the 5th electrons. Therefore, you pair it with another electron here. When you have 6 electrons, first you have 1, 2, 3, 4. Now you are remaining with 2. Then you can say, you know what? I want one of them to pair with this, the other to pair with this. So whenever you have 6 valence electrons, you have 2 pairs of electrons. In that case, you can form a chemical bond by making another pair here and another pair here. So valence electrons of 6 can form 2 chemical bonds. Valence electrons of 7, we have 3 pairs and 1 unpaired electron. And because of that, we can form only a single chemical bond here to complete the pairing process. Groups 8, everything is already paired. That's why normally group 8 elements are not reactive. They don't want to form chemical bonds. Only in special cases can we form chemical bonds, when we expand, what we call expanded octet, which we will see later. But for now, let's say that group 8 elements do not form chemical bonds because all the electrons are paired in them. Now, let's take 2 of these elements. Let's say we have phosphorus, which has 5 electrons, a single pair, and 1, 2, 3 unpaired electrons. If you want phosphorus to form a chemical bond, you need to bring in 1, 2, 3 more electrons so that you complete the pairing process. So what do we do? I have phosphorus. The phosphorus needs 3 more electrons. Therefore, it can form 3 chemical bonds. I have chlorine. Chlorine needs 1 more electron here to complete the pairing. Therefore, it can form only 1 chemical bond. So if I am bonding chlorine and phosphorus, I'll need 3 of these, because this one goes to pair here. I'll need another one to pair here. I'll need a third one to pair here. This will still be unpaired. So what do we have? So completing a pair, completing a pair, completing a pair. This one is this. So because it's already unpaired, it's not going to form a chemical bond. This is what we call a Lewis dot diagram, or a Lewis dot structure. What about boron and hydrogen? So boron has 1, 2, 3. unpaired electrons. So it's going to form 3 chemical bonds. So boron needs 3 more electrons. It can form 3 chemical bonds. So we are saying boron does not have what we call an octet. Octet means we need to have 8 electrons on the outer shell. Instead, it is complete when it has 6 electrons, because if we have a pair here, pair, we'll have 6 electrons. In that case, it is known as a sextet. So hydrogen needs 1 more electron. It can form 1 chemical bond. Hydrogen does not have an octet. Instead, it has what we call a duet. When it has 2 electrons here, it is complete. So what do? This will pair here. We need another one to pair here. We need another one to pair here. So this is what we are going to have. So this is the Lewis diagram of boron and hydrogen. The 3 hydrogen atoms combine with 1 boron atom. So there are 3 hydrogen atoms and 1 boron atom. In this case, our boron will be the central atom because we have 3 of these. What about hydrogen and oxygen? We have oxygen. Oxygen has 2 pairs and 2 unpaired electrons. Hydrogen has a single electron. So this hydrogen will complete a pair here. Another hydrogen will complete a pair here. In the end, we'll have oxygen, hydrogen here. This pair is a chemical bond. This other pair is also a chemical bond. This is the Lewis diagram of water. Silicon and chlorine. Silicon is in group 4, so has 4 valence electrons. These are the outer shell electrons. And these electrons do not pair. So silicon has 4 unpaired electrons. It needs 4 more electrons to complete the octet, that is to have 8 electrons on its outer shell. So it gets these from chlorine. Chlorine only needs 1 electron. So what it means, we need 4 of these to complete the octet on this one. So in the end, we have a Lewis diagram of chlorine. So this one takes 1 electron, another one here goes here, a third one goes here, and the fourth one goes here. 4 chlorine atoms combine with 1 silicon atom. There are 4 chlorine atoms and 1 silicon atom. Therefore, silicon will be our central atom. We go all the way to carbon and oxygen. Carbon is like silicon. It has 4 unpaired electrons in its outer shell that we call the valence electrons. Oxygen has 2 unpaired electrons in its outer shell. So these are the ones that are going to form chemical bonds. These ones will not form chemical bonds because they are already paired. So how do we combine them? 2 oxygen will combine with 1 carbon atom because carbon needs 1, 2, 3, 4. Oxygen can offer only 1, 2. So we need 2 of these to achieve 4 chemical bonds on the carbon. So this is what we are going to do. So these are the 1, 2. These are the unpaired electrons. This electron is here. This electron is here. And carbon is bringing in these electrons. So this is a chemical bond on its own, a chemical bond on its own, a chemical bond here, another chemical bond here. So some important terms are a bonding pair and a lone pair. So a bonding pair and a lone pair. A lone pair sometimes is known as a non-bonding pair. So you can see this pair of electrons is within a chemical bond, so we call it a bonding pair. This pair of electrons is not in a chemical bond, so it is a lone pair. As you can see here, all the electrons here are bonding pairs, while here it's only 3 pairs of electrons that are bonding and 1 is a lone pair. So lastly, we talk about the dot and stick diagrams. What we have been looking is the dot diagrams, but now we have dot and stick diagrams. So this is the dot diagram, but each chemical bond can be turned into a stick. So this is one chemical bond, one chemical bond, one chemical bond. So instead of drawing dots here, you can put sticks, but you still need lone pairs are still shown. As you can see, these are lone pairs. These are bonding pairs. Only bonding pairs have sticks. Lewis dot diagrams, Lewis dot and stick diagram. The stick represents a chemical bond. So this is the dot diagram. This is known as dot and cross diagram, but it's like a dot diagram. But you can turn it into stick. So as I said, this is a chemical bond, chemical bond, chemical bond, chemical bond. Each chemical bond is 2 electrons or a pair of electrons. If we look at nitrogen gas, we can say this is pair 1, this is pair 2, this is pair 3. So that pair will form a chemical bond, this pair will form a chemical bond, and this pair will form a third chemical bond. So you can show in terms of the chemical bonds, you can take all these and pair the electrons and put them on one side. So we say pair 1, 2, 3. Or you can just use a stick, 1, 2, 3. And these non-bonding pairs, you put them as far apart as possible. So this is a triple chemical bond. This is a double chemical bond. So this is a chemical bond for this. The ethene, here we are showing it as sticks. Ethane has 1, 2, 3 pairs. 3 pairs means 3 chemical bonds. So you just turn the pairs into 1, 2, 3 chemical bonds. So please check the video assignment on chemical bonds, and then we'll continue on this chemical bonding in class, and in the lab when we do dry lab 3, we'll focus also on the chemical bond and more on diagrams, the molecular shapes and molecular geometry. Thank you.